Hello, my name is Adrian Samuel, and I'll be presenting the heartbeat acquisition system for my project for medical electronics. So, to go through the steps, basically, the very first step is the acoustic sound that is being taken in by the heart through the microphone. Then, afterwards, it will pass through a low pass filter. Then, it will go through an audio amplification, and it will be outputted through the speaker. So first thing is that because of the stethoscope, it picks up sound vibrations from the heart, and it is then converted into mechanical vibrations. Then at the second step, the preamplifier and microphone, the microphone will pick up those sound signals, and then they will turn it into electrical signals. Then the amplifier will amplify the weak electrical sound to a suitable, the appropriate level for further application through driving the speaker at the end. Then for the third step, the low pass filter. At this stage, the preamplifier is filtered to remove high frequency noises from other sources or electronic interference. And then last, the fourth step, audio amplification. The line from the low pass filter, the signal, is then boosted to an appropriate level to match the requirements of the external device, such as the speaker, for clear and disruption-free audio. Then lastly, for step 5, the output signal is then converted from electricals to sound vibrations, thus allowing the user to listen to the heartbeat from the speaker. So starting, taking a look at the schematic, we can see over here that I have boxed up the 4 stages as such. So the red is the preamplifier stage, and the second is the closed loop non-inverting amplifier, and then the third is the active filter stage, and then lastly we have the audio amplifier as the last box. Starting with the preamplifier stage, so we start off at C1, the capacitor. We have C1 and C4, and both of those capacitors block out DC voltage from the input, and they only allow AC voltage to pass through. Then on the bottom, we can see that we have a voltage divider. So the voltage divider is 2 resistors, R6 and R5, both of equal value, both connected to VCC and ground. And using VDR, voltage divider rule, we can find that the voltage going out is half of VCC. And in this case, VCC is 9, so therefore the voltage going out is 4.5 volts. And the reason why we have a DC voltage blocker is because if any DC input, like offset, is put into the thing and amplified, it can shift the entire output signal up or down, so reducing the usable range of the amplifier, which is why we have to block out the DC input. Then next we take a look at the IC chip and the pass band filter. So the op amp is acting as a differential amplifier, amplifying the difference between the signal entering from the inverting and non-inverting sides. And then next we have the pass band filter at the bottom. So as we can see here, the pass band filter is comprised with the C2, R2, R3, and C3. So this pass band filter is used to allow only a specific band of frequency to pass through while rejecting all other frequencies outside of this range. And if we were to, I have a graph here I can show you. So this is an example of what it can be. So let's say the peak voltage is 15, then we minus 3 decibels, and then there are 2 intersections. The first intersection will be the lower cutoff frequency, and the second intersection will be the higher cutoff frequency. And those 2 frequencies will make up the bandwidth. And so we have a pass band gain formula, and which is 1 plus R2 over R3, and we get 23. This is my waveform for I put it at 400 millivolts, and then my frequency was 10 hertz. And as you can see, my VPP for the output is 3.24 volts, and that gain is around 10. And continuing with different frequencies, you can see that the gain will increase and decrease. So it will peak at around 100 hertz, and then it will decrease. So it will form a graph. So moving on, I'll be talking about the next stage, which is the closed loop non-inverting amplifier. So starting from the left, the C4 also again blocks DC input, only allowing AC. And then there's R4. R4 actually reduces the current entering the pin 6 of the IC from the preamplifier stage. So ICB1B is a non-inverting feedback loop op-amp. A piece of the output is returned to the input, so therefore there is a 180 degree out of phase. And between pin 6 and pin 7, there is a potentiometer which controls the amount of feedback. Changing the amount of resistance also controls the feedback resistance RF, which will affect the gain of the amplifier as well. Increased negative feedback results in linear amplification of the output, which reduces distortion, something that we've covered in the notes before in last year. And lastly, we have the voltage divider at the top at pin 5. And here is my footage for the TP2, TP3. So what occurs in my TP2 and TP3 is that as I turn the potentiometer, I can see that the gain increases, and once the gain increases, it results in the cut off of the top and bottom of the waveform. So as you can see, the top and the bottom are flat, so it becomes square. And this is because the gain is really high and the waveform is out of range. Turning it back also returns it back to a normal sine waveform. Moving forward, we move on to the active filter stage. So starting from the left, we have C5 blocking the DC input, also only allowing AC. Then we have another voltage divider pumping in 4.5 volts. And then everything else forms a Sallen-Key second order low pass filter. So a low pass filter refers to a filter that only allows low hertz to pass through while rejecting the high frequencies. The lowest hertz that can pass through is 0 hertz, the DC signal. So for bandwidth, FH minus FL equals to FH minus 0 hertz, so the bandwidth is just FC, which is the frequency cutoff. And the second order in the Sallen-Key second order refers to there being 2 RC connections. This is at 20 hertz at 3.36 volts.
Gain is 1.
So from the table given here, this is the results from the part TP3, TP4. So what occurs is that at low frequencies, the gain is 1. So therefore, the dB is 0. And then as I increase the frequency, the gain decreases and AV goes into negative. As we know, minus 3 dB is the cutoff point. Thus, everything before AV equals to minus 3 is pass band, and everything beyond is stop band. At low frequencies, 20 hertz to 50 hertz, the V in and V out are both the same, so therefore the gain is 1. And so these frequencies, low, pass through without any attenuation, which refers to decrease in dB, decibels. So from 100 to 500 hertz, gain is beginning to decrease. So this marks the beginning of the roll-off filter. Filter roll-off. But this is still higher than minus 3 decibels. So thus they are still within the pass band. Then from 800 hertz onwards, there's very clear attenuation. The exponential gain drops from 0.6 to 0.04, showing that the high frequencies are attenuated, only allowing low frequency to pass through. You can see from the graph that at the low frequencies, the gain in decibels is relatively unattenuated, unaffected, and only towards the 700 mark does it really start to roll off. And at 700 is the point where gain is -3 decibels, so thus that is the cutoff frequency. 700 is our cutoff frequency, and thus the bandwidth is 700. Moving on to the lab portion. So between my TP3 and TP4, at low frequencies, this one is 100. I have exact gain, so it's almost 1-to-1. And then once I make the frequency go up to 1000, you can see that my output becomes 240 millivolts, so it becomes smaller than the input, so there's a negative gain. And then lastly, I'd like to talk about the audio amplifier stage. So starting from the right again, you can see that we start with a potentiometer. So this potentiometer consists of a slider, which is in the middle. So when the slider is closer towards the E port, the highest input is inputted into the IC, because S is connected to the highest potential point. And when S is connected to A, there is 0 input, since it's connected to the lower potential point, which is ground la. The potentiometer acts as a variable voltage divider, controlling the amount of amplitude of input signal, allowing adjustments of volume for the output audio. And then the IC LM36N1 is an audio amplifier, which has high audio gain and provides clear audio output with low distortion. Then once again, the C13 blocks DC signal, only allowing AC. So the high pass filter on the left side is an RC network that improves stability of the amplifier by dampening low frequency outputs. Only high frequency outputs fall across the resistor and is relatively unaffected. So the formula is F equals to 1/2 pi RC, which is R17 and C15. And lastly, I'd like to show you my part TP4 and 5. Starting from the lowest setting on the potentiometer and slowly turning, you can see that the waveform generated turns from a flat line to a sine and finally to a square waveform. And then on the final end at the speaker, it'll convert the digital signals into sound vibrations, and at the other end the user can hear. So thank you for listening to my presentation, and God bless.